So let me go ahead then and introduce our two speakers. They are both board members of the Geologists of Jackson Hole, which we're very pleased and proud to have them fill those roles for us. Cynthia Blankenship is full-time resident of Teton County, has bachelor's and master's degrees in geology from Duke and Rice, respectively. Parent of 3 children, lifetime learner, she says, and she has 3 decades of corporate experience with British Petroleum. Over half of that, which was in management positions of varying and increasing responsibilities. She and family moved to Jackson, Teton Village actually, in 2016, and a multitude of hobbies: reading, geology, hiking, biking, Nordic skiing, downhill skiing, yoga, cooking, traveling. I'm sure there's more. Mike Scher is, again, a board member of Geologists of Jackson Hole. He's a bachelor's in science in chemistry from Trinity College. He's worked as a science teacher in both middle and high schools. He also worked for several years in outdoor education. His last employment, and I think the one that enabled him to and family move here, was running a small chemical manufacturing company. So again, Mike is a long-serving member of the Geologists of Jackson Hole board. He's worked in many of our local schools, leading field trips and teaching geology. And he has led a number of Geologists of Jackson Hole field trips, and this will be his 5th public talk. So without further ado, I'm going to turn the program over to Cynthia and Mike, and thank you both. Looking forward to it.
Okay, thanks, John. So you might think I took this picture on the title slide because of the rocks, but actually, if you look at this patch of snow, there's a ski track going down there that wasn't there the month before I took this picture. So I thought that was pretty cool that somebody hiked up there and skied down that little bit. Anyway, moving on. So first of all, I'd like to acknowledge my colleagues, Mike Scher, this is the co-author of this talk, and also my hiking buddy, along with his wife, Barbara, who are incredibly avid hikers and rock finders. And also John Heberger. So between Mike and John, they have taught me just about everything I know about the Jackson Hole, and I'm sure you guys have all benefited from their knowledge as well. Also like to reference an awesome book called Creation of the Teton Landscape by David Love, John Reed, and Kenneth Pierce. Hugely helpful, as you can see all the tabs I put in there. And then the Geologic Map of the Teton Quadrangle, which you can buy from the U.S. Geological Survey, Wyoming Geological Survey, which is also extremely helpful. And then, of course, we have various internet sites, which are very helpful for pictures and so forth. So the location of our talk, of course, is the Teton Range of Western Wyoming. And what we're going to talk about is, first of all, I'll talk about the geologic setting of Jackson Hole to put everything in context. Then Mike will talk about what exactly are carbonates. So carbonates is a bucket term for limestones and dolomites. Limestones are the primary depositional sedimentary rock, and dolomites are a secondary precipitate that alters basically limestone. And then, as promised, we'll talk about where to find these outcrops and the fossils that they contain. And we'll mix that up. I'll do where to find them, and Mike will cover the fossils, since most of the fossils that we'll see today are either pictures or real examples of ones that Mike's collected over the years. Okay, so let's start with the basement rock here in Jackson Hole, the Tetons. So this brown outline is the North American Craton, a very stable piece of continental crust that is up to 4 billion years old. And in all these paleogeographic maps, what I've outlined is the state of Wyoming. So that's the red outline in all of these. And sort of deformed onto the North American Craton is this area in purple, which is actually where we are in Western Wyoming.
And it was formed by a continental collision about in the Archean, so 2.6 to 2.8 billion years ago, that essentially created metamorphic gneiss. And then after that, about 2.5 billion years ago, we had the granitic intrusions. So think that Mount Moran. And quite a bit later, only 755 million years ago, is when all those big dramatic black diabase dikes that you see vertically cutting Mount Moran and other mountains. So those together, all these rocks form the basement that the rocks we're going to talk about were deposited on top of. So for the next diagram, you're going to have to do like this Gary Larson Far Side cartoon and kind of do one of these numbers like this. So that's because it's another paleogeographic map, but paleogeographic map is oriented in kind of modern day position of the United States. So you can see Texas here and Wyoming in red and Montana. But at this time, because of continental drift and the position of the continents 100 or 500 million years ago, the equator was actually along this yellow line here, and north was to the left. And so, as I mentioned, all these the dikes and the granitic and metamorphic rocks were in place. And then during the Cambrian was when we have established a sort of a passive margin on the western side of this stable Craton. And a passive margin is basically it's not a converging margin, it's just a margin that's drifting away from a spreading center somewhere. And it's setting up our shallow seas that we're going to see are a feature of the Cambrian through Mississippian, which are the rocks that we're going to talk about that were deposited. These carbonate rocks were deposited in these shallow seas. So next, we're going to zoom in on the Phanerozoic, so the more recent part of this timeline that starts in the Cambrian. So here we have the Cambrian through actually the present day, the Quaternary, and some features here of each of these, brief features of each of these periods are the Cambrian is very early animals, the very first fish, which were really primitive, no jaws, just basically suckerfish. And then we had more diversification in the Ordovician. We have no rocks of the Silurian age in Jackson Hole area, but that's when plants were starting to form on land. And then we have the Devonian, which was a big diversification in fish life, first the amphibians. We had the Carboniferous, which is made up of the bottom part is the Mississippian and the upper part is the Pennsylvanian. And then we have the Permian, which is where reptiles start diversifying, and then a big extinction between the Permian and the Triassic called the Permo-Triassic extinction. And then in the Triassic, we have the first dinosaurs and first mammals that then again diversify until the end of the Cretaceous, when we have another big extinction at the Cretaceous and Tertiary boundary. And that's when the dinosaurs go extinct. And then we have the age of the mammals in the Tertiary, and then the humans arrive on the scene at the very, sort of the width of this line. Okay, so that's kind of the timeline that we're going to be looking at. And the rocks that we're going to be I should talk about some conventions first. So in geologic terminology or map making, especially cross sections and so forth, generally limestones are colored blue, reminiscent of their depositional environment in the shallow marine setting. And then sandstones and shales are colored in oranges and shades of yellow and so forth. So the rocks that we're going to be looking at are, the oldest ones are these Cambrian rocks, which is a collection of the Flathead Sandstone and the Grovant group, which is composed of the Woolsey Shale, Death Canyon Limestone, Park Shale, and Gallatin Limestone. And let me explain this terminology here at the end of each of the names. That's geologic terminology, and it starts with a capital letter for the age. And so this is the Cambrian, and in particular, the Cambrian has a little hash through it. So we have, these are the mapped units. So the Flathead Sandstone and the Woolsey Shale are mapped together. So it's Cambrian, Woolsey, Flathead. And then we have Death Canyon limestone, so it's Cambrian Death Canyon. And again, the Gallatin and Park Shale are mapped together, so it's Cambrian Gallatin Park Shale. And then we have a gap in the rock record until the middle Ordovician or so. And then we have the deposition of the Bighorn Dolomite, which is Ordovician. So it's O, capital O, Ordovician, B for Bighorn Dolomite. And then we have another big gap, as I mentioned, the Silurian does not have a rock record here. And then neither does the early Devonian until we get to the Darby Dolomite at the end of the Devonian. So Devonian Darby. And then finally, the lower Carboniferous called the Mississippian, we saw a deposition of Madison limestone, Mississippian Madison. So you can see that we have a good representation of this, of a lot of the Paleozoic, but there are some big gaps as well. And some of these other rocks, younger rocks, are represented here in the Tetons, but we will not talk about them today. The next major events that happened are the mountain building events, starting with the Sevier orogeny and the Laramide orogeny, and then the Basin and Range. So these are orogeny is a fancy term for mountain building event. And these are the mountain building events that created the Rocky Mountains. And we, of course, have the Tetons, which is arguably part of the Basin and Range events. And then finally, the Yellowstone caldera track, which started, 16 million years ago, way over in Western Idaho, and marched steadily to its current position in Yellowstone National Park. And then after all of that, we have the, we have the glacial events. So the Bull Lake glaciation and then the Pinedale glaciation. So that's a very brief overview of the bigger picture of Jackson Hole Mountain Resort. And I think it's worth pointing out also that up until these mountain building events, all of these previously deposited rocks were basically flat. So they were deposited on top of each other, kind of like layer cakes. And it wasn't till quite recently that they started to be moved and formed into mountains. So now I'd like to, well, first of all, I need to see my own screen. So better, there we go. I'd like to transition and talk about the geologic map of Jackson Hole or the Tetons. And it's hard to read. So this is the geologic map. Again, it's the big map in the back of the book, Creation of the Teton Landscape. It's a fold out. This isn't just a photo of it. It's a little hard to get your eye in. So I've also put a more standard ArcGIS map next to it. So this red outline on the ArcGIS map is roughly the same outline as this entire geologic map. So what we have here is Jackson Lake. We have the Snake River coming out here and coming down through the middle of Jackson Hole. We have Phelps Lake. We have the town of Jackson, I-22 coming in. So here's I-22, here's the town of Jackson. We have Phelps Lake, which is here, and Jackson Lake, which is here. And then, of course, this is the Teton Range, and this boundary of the Teton Range is the Teton Fault. And you can see that, which is this red trace running along the edge of the mountain right here. So hopefully that gets you oriented a bit. Now let's look at the geologic map in a little bit more detail. And as we go through this talk, what we're going to be focusing more and more on is this southern part of the map, which is in the Jackson Hole Mountain Resort. And the reason is because we promised to talk about accessible outcrops. And the Jackson Hole Mountain Resort has this really neat feature, which are called ski lifts that bring you right up to the outcrops. So it's very, very accessible. So just again, here's the Teton Fault in red. This is the top of the Jackson Hole Mountain Resort tram. And just to reference, this is Granite Canyon. And that kind of brings me to a point about how to read this map. So this is a little cartoon, a block diagram cartoon that shows The pink on this map is all that Precambrian basement that we talked about from the Archean up through the Black Dikes. The Black Dikes are actually shown in these green lines. And then sitting on top of the Precambrian, and for many millions of years, it was basically flat-lying stratigraphy. So this Cambrian through Mississippian, these rocks that we're going to talk about were deposited and were flat. And then when mountain building occurred and we have the normal Teton normal fault, we set up a situation because of the deformation where the Teton normal fault, the valley of Jackson Hole is going down, so that's down thrown, and the Teton Mountains are going up, so they're up thrown. And because of that motion, there is dip that's created. And so these Cambrian, well, all these strata here, and this is the fault. So this plane here is the fault. All these strata are dipping to the west toward Idaho. And this symbol here is a map symbol showing what's called the strike, which is north-south, and then the dip, which is to the west of these rocks. And so what happens when these rocks get uplifted is they start to get eroded as they get uplifted. And so what we have then is a valley that's created, one of these canyons for example, in Grand Teton National Park. And because of this erosion, what gets exposed in the valley is the underlying Precambrian. And so you get this pattern of this pink Precambrian going up into the canyons. And so you can see that very nicely here in Granite Canyon, where the pink goes way back into the Tetons, and you can see it here in Open Canyon and Death Canyon and so forth. So all of these pink fingers that go into the Cambrian through Mississippian strata are these canyons that have been eroded. Okay. So now, as I promised, let's zoom in on the Jackson Hole Mountain Resort area. And again, we're very fortunate in that toward the top of the mountain at Jackson Hole Mountain Resort, we can walk up to quite easily outcrops that range from the Flathead Sandstone all the way through the Darby Dolomite. And if you're willing to scramble a bit and go off trail, you can also get up to the Madison Limestone. But if you don't want to do that, there's a really cool alternative, which is that the Madison Limestone occurs on the north end of Blacktail Butte. So this is just near Moose, the turnoff to Moose. There's a parking lot there. It's a very famous climbing area. And the Madison Limestone is vertical here. And you can drive up to the parking lot, and in a short walk, you can get to the, put your hands on the Madison. Okay, so here's a lovely picture of my husband playing golf, about to tee off. And I'm really glad I took this picture because it's also a lovely view of almost the entire Jackson Hole Mountain Resort. And that's what we'll zoom in on now. So from the valley, from Jackson Hole, from the Snake River Valley, what we see, this entire mountain is almost entirely Paleozoic basement. And to sort of orient you, so here's Cody Peak, which we looked at, that was on the introductory slide. This is the Green River Overlook, which we'll talk about later. Here's the top of the tram, and you can barely see some of the tram towers there that hold up the cables. And then this right here is the top of the Bridger Gondola. So that's also accessible. Both the gondola and the tram are accessible all summer. And so the strata that we're interested in are really above this red dashed line. So below this red dashed line are all those pink Precambrian rocks. And the Cambrian through Mississippian are what you see here as like the icing on the cake. So if you do take the tram to the top and you take a picture, as Mike did, you can see the entire Cambrian through Mississippian section. So this is taken very near the top of the tram. Starting out in the Cambrian, we've got the Cambrian Gallatin limestone, which is this piece here, the Death Canyon limestone. These rocks are 500 million years old and about 1,000 feet thick. Sitting on top of that, so this is a kind of characteristic cliff, shale, finer grain sediment break, and then cliff. The Bighorn Dolomite is a major cliff former. It's Ordovician in age, so Ordovician Bighorn, 450 or so million years, 450 feet thick. Then we come up section to the Devonian, Darby, and it is 370 million years old and 350 feet thick. It is not a cliff former, it is a slope former. And it's a good way to recognize it. And then finally, capping everything off, we have the Mississippian Madison limestone, which is really very thick, over 1,000 feet thick. And it is also a cliff-ish former, not quite as dramatic as the Bighorn, but definitely a cliff former. Okay, and so just to show you how ubiquitous these rocks are, if you look across the valley at Sheep Mountain, locally known as Sleeping Indian, you can see the same pattern repeated. So the Sleeping Indian's nose and belly is composed of a Madison limestone. Underneath that is the Darby, which is the not cliff former, the slope former. And then the headdress piece is the Bighorn Dolomite. And again, below that, you can see this Gallatin and Death Canyon limestone doublet here. So with that kind of introduction to the big picture, I'd like to turn it over to Mike, who's going to talk about the nature of limestones and dolomites and their chemistry and so forth.
So, thank you, Cynthia. So, can I advance the slides? Yeah.
No, I will. I'll just say next slide.
Okay, thank you. So, this little thin veneer on top of some of the Tetons, not all, just the southern, northern, and western part, these limestones and dolomites are basically about 10% of the rocks that you'll find on the surface of the earth. And most of these are formed biologically, and we're going to talk about how they're actually formed. These are great methods of storing carbon dioxide, and they are part of the global carbon cycle. The carbonate part is made of carbon dioxide. These rocks are soluble. They are very permeable and porous, and this is why they're such good reservoirs, both for water and hydrocarbons. They also dissolve with acids, such as this hydrochloric acid, which we're going to get to play with later. And they are also soluble in acid rain. Rain actually has a pH under 7, making it acidic. As the water comes through the atmosphere, it picks up carbon dioxide. It makes weak carbonic acid, and it also will pick up any sulfates or sulfur dioxide to make sulfuric acid, which we used to pump a lot of that out until they put scrubbers on the coal plants. Commercially, this is used for making buildings, concrete, pigments, and even the calcium that you might take for your bones. Next slide, Cynthia. So limestone can be formed organically or inorganically. Organically means biologically based. And stromatolites, which we're going to meet later, are basically these mats of cyanobacteria, and they will trap sediment because they're kind of snotty and mucousy. And as they do, they're photosynthesizing. So they want to grow through them. And as they grow through them, they trap those sediments. Their actual photosynthesis helps precipitate calcium carbonate or limestone as well, by the way they are modifying the surrounding seawater. The picture here is of a polished and cut stromatolite cut down the middle basically, so you can see how those little layers would form. And this is a small part of the limestone formed. Coral reefs, which have been around for 450 million years, and we'll see a picture of an Ordovician one, are a great way to capture calcium carbonate or limestone. The picture here is actually a fossil coral called Syringipora or organ pipe coral, named after those very thin little tubes. And each of those tubes was the home for an organism, and it made that home by pulling calcium carbonate out of the water, basically making its own limestone, which became its house. Next slide. So in addition, you can have shells, which are also made of calcium carbonate. And this fossil here has a couple of horn corals in it, one on the far right, and then the rest of those shells are brachiopods. Yes, thank you. And basically, this is the large version of capturing calcium carbonate and making limestone. And this fossil is also an actual fossil collected from the Madison limestone. So it shows the bottom of an ocean floor 350 million years ago. The predominant, the majority of the limestone is actually formed from these very small shells. These are single-celled organisms. So these are very, very tiny things, but there are billions of these foraminifera and diatoms. And as they die and fall to the bottom, they form the sort of limestone mud and ooze, which is later lithified, turned into rock by pressure. And there'll be billions of them. So when you have one of these with all these shells in it, the matrix is made up of these very tiny, small things. Next slide, Cynthia. Inorganically, you can get limestone forming as well. So the first ones I discussed were all biological in origin. These are chemical or physical precipitations. Many of you, I'm sure, are familiar with Mammoth Hot Springs, the large and wonderful travertine terraces in the north of Yellowstone. These are formed because this same Madison limestone that Cynthia talked about at the top of Cody Peak, the top of Sheep Mountain, is actually underground below the north end of Yellowstone. And as groundwater, which lands in the form of rain and snow, percolates down, is warmed by the underlying warmer rock, and then comes back up through the Madison. Remember, it's very porous. That warm and hot water can actually dissolve the limestone. It reaches the surface where it's cold and it precipitates, and it's no longer under pressure. It now precipitates out all that limestone as travertine. So when you go to Mammoth, you're actually looking at dissolved 350 million year old limestone that has been reprecipitated on the surface. Also, if you're in a cave, stalactites and stalagmites are another obvious source of forming limestone. They're not going to form a lot compared to these other processes. Oids are these very small, and these are like 2 millimeter large little balls that are formed in shallow, warm marine environments. Basically, you have a nucleation point, and then you can get the calcium carbonate precipitating onto that little point. And lastly, if you're very lucky, you can find a vug or a void in a rock filled with calcium carbonate crystals, in which case you are very fortunate. Next slide, Cynthia. So let's do a little chemistry. Limestone is calcium carbonate, and it can crystallize and form beautiful crystals. The two more common ones are aragonite, which is the pinkish ones, and these are colored pink because they're slightly contaminated by iron oxide. They would normally be clear. And then the other very common form, and I've found these shaped crystals, these what they call scalahedrons. The common name is dogtooth calcite. And you can actually find these occasionally in the Tetons in voids where the calcium carbonate has had the right conditions to crystallize it. Mostly what we find, though, is the limestone that you see in the normal rock. Limestone is a very soft rock. The hardness scale for minerals runs from 1 to 10, with 10 being a diamond, 9 being carborundum. This is a 3, so it's a very soft, easily eroded and carved rock. Next slide, please. So dolomite is, as Cynthia mentioned earlier, a secondary formation. So we start with limestone, calcium carbonate, and you get an infusion of magnesium-rich water, and that's represented in the equation by the Mg+2. This is not metallic magnesium. This is a magnesium ion dissolved in the water, because calcium and magnesium have basically very, very similar chemical properties. They can interchange, and so the magnesium will replace some of the calcium and form this calcium magnesium carbonate, which we call dolomite. It's not always a one-to-one replacement. It's a whole range of possibilities that you see in the natural world. Next slide. So when you're out there and you're looking at the rock, how do you know what it is? Well, hopefully you have your vial of hydrochloric acid. This is 10% HCl. Try not to get it on your skin. And I'm gonna, maybe Brent, you can highlight me for this, if possible. Thank you. So this is the same fossil you saw earlier. I'm not going to put the acid on the front. I'm going to put it on the back. And I'm going to hope that you can see this and that I don't drip it on my computer. But what we're looking for is a reaction where the hydrochloric acid is going to do that. It's going to foam like crazy. And what's happening is the acid is reacting. You can go back to the slide now, Brent.
That didn't have, okay.
Oh, perfect. Okay. So what you saw was actually breaking down the calcium carbonate into carbon dioxide, water, and then calcium and chloride ions. And that fizzing, that's the carbon dioxide coming off. And it's a very, very vigorous reaction. This is why you do not put marble in your kitchen, because marble has the same chemical formula as limestone. It's calcium carbonate. It's just been heated, squeezed, and the crystals have been rearranged, but it will react with acids. And there's lots of acid in food. All the fruits, wine, lemon juice, you name it, vinegar, this is why they use granite or synthetic materials, not limestone. Now, if I tried this with dolomite, and I actually have some dolomite here, but it doesn't, the reaction is so weak that I'm not going to show it to you. I'm just going to describe it. And basically what happens is when you drip it on, you don't see anything. You then need to scratch it with a nail or a knife or anything, even another piece of dolomite. And you will then powder the dolomite, increasing the surface area, and you will then get a weak reaction. And so that is a good field test for differentiating our dolomites and our limestones. In addition, as you saw, The limestone is often very blue. The dolomite is actually a lighter color. It's more of a light gray, but I would not use color as a diagnostic test, but I'm very comfortable using the acid as a diagnostic test. And when you try this at home, be very careful. Next slide. Yeah, there was the demo.
Okay, can everybody hear me? Brent, can you spotlight me? Great, thank you very much. So now I'm going to take you on a really quick tour of what some of these outcrops look like. So we're going to zoom in on the Jackson Hole Mountain Resort. Again, it's in this area here, and we've been looking at this map, which is from Love et al. And we're going to now look at a more detailed map, which is the Teton Quadrangle Geologic Map. But first, I want to get you oriented to that. So this is the detailed map we're going to look at. And what I've done is I've covered over the detail with the same colors as we've been looking at. So you can see this pink outline with Granite Canyon here is this pink area here. And the pink is the Paleozoic basement rock. And the lighter blue, the light blue, are the Cambrian through Mississippian rocks that we've been talking about. And then of course, here's the Teton Fault. So this is the boundary between the the Precambrian and the Quaternary sediments of Jackson Hole or the Snake River Plain. Okay, and so also what you can see under here are the trace of the Bridger gondola and the tram, the aerial tram that goes to the very top of the mountain resort. So let's look a little more detail now at the geology of the mountain resort. So here we have the full section from the Flathead Sandstone up through the Devonian Darby Dolomite. This map ends here, but just off the map here is the Cody Bowl, where you saw the pictures already of the Madison limestone, the Mississippian younger Madison limestone. All right, so let's zoom in again. And here we have, this is very, very accessible. This whole sequence of rocks from either the Bridger gondola or the tram, and I'll show you some pictures from both. But again, we have the Cambrian, the Flathead below the Woolsey, and then the Death Canyon limestone, and then the Park Shale and Gallatin limestone. And then moving up in the section, getting younger, we have the Bighorn Dolomite and then the Darby Dolomite. And off this map is the Madison limestone. So I'm going to take you now on a tour. First, we're going to do the Casper Loop, and then we're going to do the Cirque Trail, and then the Green River Overlook. So the Casper Loop, you get there by taking the Bridger gondola up to the top. The first part of the loop is quite steep. You're basically climbing up the Precambrian, but then it becomes quite flat, and it's about a 2-mile loop. So it's quite a lovely little hike. And when you start climbing up this slope here, you actually encounter the contact between the Precambrian and the first rock you find is the Flathead Sandstone. And here's a picture of it so this picture is taken, it's kind of a Flathead Sandstone rubble pile, but it's looking toward Blacktail Butte here to the east. And characteristically, it's a reddish color, sometimes yellow, sometimes pale yellow. And it very often has this beautiful cross bedding. You can see these depositional patterns from when the rock was deposited. And so this was taken about right here. And then we continue up and around. Oops, sorry, wrong way. There we go. And then you are hiking here on the Woolsey Shale. And about at this point here, you can look up, here's the Woolsey Shale in the foreground. And these spikes here, these poles are the boundary of the national forest or national park. And here you can see the Death Canyon limestone, which creates a nice outcrop, small cliff forming outcrop. Okay, and now we're going to take a hike along the Cirque Trail, and again, across all these same formations, but in addition, we'll have quite extensive and long views of Corbett's Couloir. So Corbett's Couloir is where very good skiers jump off, or I would probably commit suicide if I tried. It's a very famous ski run in the mountain resort, and it's visible from nearly this whole Cirque Trail hike. And so we're looking at Corbett. So you can see the tram here. The top of the tram is just off the picture up here. And this is all the Bighorn Dolomite, this major cliff former. And so this picture is taken from the north looking south. And so now we're going to go and we're going to take this from the top of the tram. We're going to hike down the Green River Overlook, which is about a 3.5 mile round trip hike, and not terribly steep. It's quite doable. And it's one of my favorites. It's really beautiful. And so here I am on the Green River Overlook, and I'm standing on the Bighorn Dolomite, and you can see it's this big cliff former here. So Corbett's is just on the other side of, Corbett's is actually on the other side of this over here. But here's the Bighorn Dolomite. Here's that Darby Formation, which is this gentle slope forming formation. Here's the top of the tram over here, which is where we came from. And then you can just see the edge of the Madison limestone here, which is headed up to Cody Peak. So this is Cody Bowl here. So now I'm going to turn around 90 degrees or so and show you again Cody Peak. So this is the Madison that we were looking at was just over here, and now it's this big outcrop that creates Cody Peak, and below that this slopey Darby Formation. And finally, let's just I wanted to show this because again I just turned around 90 degrees and now I'm looking the valley of Jackson Hole, and you can see in detail the Bighorn Dolomite and its kind of rough texture here, as well as all the nice jointing at this outcrop. Okay, so that was a quick, sorry, I forgot one. So again, you could either hike up here, which is, not trivial, but if you wanted to get up close to the Madison limestone, the easiest way to do that, as I mentioned earlier, is from the Blacktail Butte parking area across from Moose, and you can walk up and touch it. If you're so inclined, you could also boulder it from the very near the parking lot, or even climb it. And it's apparently a very popular place to go climbing. And in this location, the Madison is vertical. So the beds are actually vertical. Okay, so Mike, back over to you for a discussion of the fossils.
Thank you. Next slide, please. Yeah, so we're going to talk about worm burrows and stromatolites. These are and trilobites, actually. These are the fossils you'll find in the Cambrian, the oldest layer of rock. They're around 500 million years old. And this would be a worm burrow slab, which comes out of this old ocean. And this is, again, ocean floor. I want to go to the next slide. These are the stromatolites on the west slope of the Tetons. We've done a couple of field trips there. I'm sure we'll do another one. And so when you're here, you're 9,000 feet above sea level, 1,000 miles from the ocean, and you're standing literally on a Cambrian, a 500 million year old seafloor, where the soft shale has eroded to show the stromatolites in their life position and their actual life size. And so these were big mounds of cyanobacteria that grew layer by layer, like an onion growing outward. And these provided the oxygen that fueled the animal revolution then the animals turned around and ate all these stromatolites. And so now we only find them in very restricted, hostile environments, like our next slide. Like in the Bahamas, where, Cynthia, maybe with your cursor, you can show one of those stromatolite. Yes. So these are going to be very hostile saline environments where the grazers can't exist. And so you'll find stromatolites. Other places would be Salt Lake, the Great Salt Lake. And we actually had a talk about the microbial communities there. In addition, Sharks Bay, Australia was the first place that stromatolites were sort of discovered. They weren't sure they were actually still here. And then about 65 years ago, they found them. And since then, they found them all over the world, even in Yellowstone, in Octopus Hot Springs. Next slide. Cambrian worm burrows. This is a seafloor, and you can find these types of fossils up near just below Hurricane Pass is a great place to find them. And the burrows are the gray, and these are actually somewhat raised, so they're a little harder than the rock that they're in. But this is actual 500 million year old seafloor showing animal life. Next slide. So this gives us a position for the Bighorn Dolomite, which we've moved up, and our Bighorn is about 450 million years old. The again, equatorial warm tropical seas. Next slide. And so this is an actual coral reef, piece of a coral reef in this Bighorn Dolomite. And you can see the rock is a little bit grayer. Clue that it's a dolomite. If you put the acid on and scratched it, you get a reaction. And you can find these dolomite, these Ordovician reefs. They're hard to find, but you can find them in the park. If you walk up off the Crest Trail and kind of go west to the divide, you can sometimes find them. They're not easy. Next slide. The first corals appeared about in the Cambrian, misspelled. The corals that we typically find here are the horn corals, which you saw earlier. And if you just spotlight me for a second, Brent. So these are the horn corals, and they're solitary, rugose, wrinkled corals, and they are the most common fossil you're going to find there. They're also tabulate corals. You can go back to the slide and the next slide even.
Mike, can you guys hear me? Every time we do this, I
Yeah,
have
okay.
to actually restart the slideshow.
Oh, all right. Well,
So maybe we
okay.
could leave the
Yep.
the physical show and tell to the end.
And so we also find group corals called tabulate corals. Next slide. The Darby Formation is your least fossiliferous. The reason you know you're in the Darby, you're on a slope, and you find all these fossils that fell down from the Madison. Next slide. The Darby is a time of extinction, and this chart actually shows those peaks on there are 5 of the major extinction events that happened since complex life developed. And you can see one of them is right in there in the Darby. Next slide. And the Darby, our Darby is brown, and it is. It's very brown. I don't find it particularly stinky, but they say if you break it open, you can actually smell that. That's not my experience, but you can tell it's the brownest one of our members because it's filled with lots of sand and mud particles. And this also would have inhibited lots of the animal life that we're looking for, like the corals, which preserve as fossils because they already are hard and they're limestone. And the soft things we'll never find here. Next slide. So this is the Madison limestone, and this is our most fossiliferous layer. Next slide. And so these are common fossils that you will find there. The one on the left, I don't know if, does my cursor come up?
No.
Okay. Well, if you could show everyone yeah. So this is a crinoid, the crown of the crinoid, the feeding appendages, and it's sort of like a starfish attached to the stalk. So the stalk is like the arm, which is the middle slide, and then that crown is the feeding appendage, and that's an actual modern day one. And you'll be very, very lucky to find one of these crinoid crowns. I think I found about 6 in many hours of looking. Next slide. We find lots of brachiopods, which superficially resemble clams or bivalves, but they're not. They're their own phylum. You also can find gastropods or snails, is the other word. And these are quite common. Again, the reason they're common is they start as hard materials, so they're easy to preserve, easier. Next slide. Lots of beautiful corals. This is a Favicides, or honeycomb, as you would imagine would be the popular name for this. And again, this is a 350 million year old coral, and each one of those little honeycombs would have had a little polyp in it, a little animal living and making its living. Next slide. Beautiful horn corals. The one on the right, all those little ridges are called septa, and that's what the animal would have anchored itself in. Next slide. This is the last slide. We always have to end with a dog slide. And this is on Taylor, the mountain just above Coal Creek at the bottom west end of Teton Pass. Abby, my old dog on the left there, is sitting on the very top of the Madison limestone at the contact between that and the Amston. And she doesn't know it, but there's some beautiful fossils near there. But she doesn't care. She's looking for critters. And then Onyx, a couple of years later, in the same wonderful spot. Again, not paying attention to the fossils, but thank you. We hope this has been informative, and we're open to questions.
I think you're muted, John.
Yeah, all right. I'm not seeing a whole bunch of questions, at least yet. So I'll certainly invite people to type in the chat, if you would, please. Any question that you might have for Mike or Cynthia. I might just, one question is, can you be a little more specific about a good place to possibly find, some fossils, Mike or Cynthia?
Sure. The easiest place, which you can drive to, is the Blacktail Butte parking lot. These are fossils. You can easily find them there. You cannot take them home because they're in Grand Teton National Park. But you will, within 5 minutes, I've taken school groups there a number of times. within 5 minutes, you will find brachiopods, crinoid stems, and horn corals. If you want to take a longer trip and a place where you could actually collect if you wanted to, you could go to Taylor Mountain, where our dogs were pictured on the west side of Teton Pass. That's about a 2-mile walk and about 1,000 vertical feet up to where you can start to find, you'll find fossils that have rolled down almost the whole walk, but they're concentrated up high where you actually make the climb up to the mountain.
Okay. Question came in about where would be a good place to see the Teton Fault, perhaps in the park and at the village.
So
Yeah, go ahead.
would you like me to answer that, or
Well, actually, you can see that the Teton Fault is quite easily seen in the Jackson Hole Mountain Resort. If you take in the summertime, you can go in the wintertime too. There's a ski run called Union Pass Traverse, and it runs along the bottom of the Hobacks. And you'll right along there, you'll see some very steep cuts. And in fact, along some of those hiking trails, there is where they dug a trench underneath the tram line on lower tram line. No, it's not on lower tram line, is it? No, it's just to the south of lower tram line, and where they trenched the fault itself. I do have some pictures, but they're not in my slide deck, so I can't pull them out quickly.
I would recommend the best place, and you can actually see the fault scarp itself, which is, you can actually see the scar of the fault, where the last place the fault has moved. If you are driving to String Lake, just before you get to that right-hand turn, there's a pullout, which is labeled, I think, horse trailers, or that's where the horse people would park. And if you go there in the afternoon and look right at the mountain, and there's even a sign there, it's one of the few geologic signs in the park, and it shows you the actual fault scarp there above String Lake. And it's very prominent. It's about 50 feet high, and it's the last place the fault has moved since deglaciation, so 13,000 years. And there's a sign there to help you find it.
Just a comment that was made is that it would really be neat for geologists at Jackson Hole to lead a field trip up above the tram. And somebody else commented, and I saw this as well, apparently the tram's not going to be run this summer.
Yeah.
So
you have to hike up from Bridger. Not terrible.
Yeah, that's one way to do it. One question that came in is about Blacktail Butte and the layers that are there. And there was a question about why those layers are there. Is faulting part of the reason?
Well, best sort of theory about that is that Blacktail Butte is a slide block that came off the Tetons. In other words, an enormous chunk of earth that slid down from the Tetons and then rotated as it came across the valley to that 90-degree position where it is. Because when you're at Blacktail Butte, the Madison is oriented 90 degrees to its quote normal orientation that you would see on Sheep Mountain or on Cody Peak or one of those other places. And John, feel free to elaborate on that as well.
No, I think that's there's a lot of Sturm und Drang about how a lot of things are formed. That's actually the explanation that I prefer, is that it's a slide block. It's hard to see it like East and West Grovant Butte or Miller Butte as a rotated fault block, which is the other possibility, but perhaps not as likely. So, the Tetons got a lot of elevation on them. Something falls off, it's going to come down a long way. Mike, a question for you, and it was just asking, maybe you you did address this, but maybe you could be a little more specific about how much time and effort it took to find those 6 crinoid heads.
Well, first of all, I have to give credit for this one to my wife. I didn't find it, she did. If you're looking in the Madison, you will certainly find crinoid stems. Sometimes they're going to be little pieces, almost the thickness of like twice a pencil point. I mean, they can be really teeny, or they can almost be as thick as your finger. The stems preserve much more easily. I mean, again, you have to remember that every fossil we find here is hundreds of millions of years old and has been buried by thousands, many thousands of feet of sediment sitting on top of it. The Madison, even here in the Tetons, has, doesn't have as much here in the Tetons, but that's because those other Mesozoic, in other words, Jurassic, Cretaceous, Triassic layers have been eroded off. But there was another over a mile of sediment on top of that has been eroded off. So these things have been compressed for a long time. But the best place to find the crowns that I have had success in is in Darby Canyon, up above Wind Cave. That's where I've had the most success. But I've been there many times and not found a single one. Every time you go out, you can find something different. I found trilobite tracks there and never seen them again or before. So it's kind of luck of the draw, but they are if you find 100 fossils, well, probably not one of them will be a crown. If you find 1,000, maybe 1 or 2 will.
Somebody's asked if you, Mike, real quick, somebody's asked if you could hold up that crinoid head against crown for people to see.
Yes, and so these are the arms right here. This is the whole, that whole thing is the crown. The stem would have come down from there, but it's gone. It didn't preserve in this rock. And even this crown is highly eroded.
So I was just going to say that the most common way you find crinoids is actually disaggregated parts of their stem, and they just look like little Cheerios. So whenever you see a little Cheerio in a rock, most likely it's a piece of a crinoid stem, and they're incredibly common.
Right, and this gap right here is where a crinoid stem would have been, but it has eroded and fallen out. And there are little crinoid stems on this side, but they're so small that you'd have to have it right up to your face to see them.
Okay, to either of you, or maybe both of you, what's sort of the time frame to create limestone? Is it fast? Is it slow? How long does it take to form limestone?
Well, that's a good question. So coral reefs are basically limestone that are being created in real time. And we know that, for example, coral reefs keep up with rising sea levels on atolls and so forth. So, I would say a centimeter a year, something like that, maybe but the deep water or deeper water muds, it's being formed constantly. But those are very condensed sections. So, fairly long time frame locked up in a deep water mud, thousands of years.
And you generally need a little bit of compression. In other words, stuff on top to have it lithify and actually move from mud to rock. So,
yeah.
So, but yeah, I mean, coral reefs are a limestone and they are forming in real time. Question about the trails, Cynthia, that you showed. Are those treks actually on actual trails, or are they just sort of a rough route?
No, they're actual trails. Get yourself a Jackson Hole Mountain Resort hiking map this summer or go online. And they're all the trails that I named in the slides are actual name trails that are signed and they're in incredibly good shape. The mountain resort keeps them up all summer. They're you don't need any special equipment. Sneakers are fine. And none of them are dangerous in any way. So it's the Casper Loop above the Bridger. It's the Cirque Trail. Well, that's the top part of that. If you go straight up the Dolby, Bighorn Dolomite and so forth, it's a little more challenging. But you can always go around up the surface road. And then the Green River Overlook is a lovely trail. I just really enjoy that one.
Another question was about the Italian Dolomites and their age. How do those compare to the age of the formations that you've been talking about?
I don't know, but I do know that the name Dolomite comes from the Dolomites. There's a range called the Dolomites in Italy, which I think is what the question is about. But I'm not sure what the age is. I'm sorry.
They are Paleozoic, that I know. But I don't remember the age either. No. Let's see. Question is, what formation is on top of Mount Moran?
That would be Flathead Sandstone. And the other place where that same phenomena happens is Jackson Peak, which is the prominent peak to the south of Sheep Mountain or Sleeping Indian, and is a much easier ascent than Mount Moran. And the top 50 feet, vertical 50 feet or so, are Flathead Sandstone there. So you're looking at the very beginning of the Paleozoic rocks.
I think so. Mike, correct me if I'm wrong, but I think that Flathead Sandstone it's just a little bit on the top of Mount Moran. You can actually see it from the road.
Yes, you can.
And I think that it's a great example of the law of superposition in geology, because you've got Mount Moran and then you got a black diabase dike and then an unconformity, and on top of both of those is the Flathead Sandstone.
Yes, correct.
Which is super
all
cool.
three. Yes.
Here's a sort of related to that, and it's about volcanics. And so while crossing the Teton Pass, you see lots of volcanics, which I presume are much younger. So why are they lower in elevation?
Well, the volcanics are much younger. Best dating is probably 8 million years, rough numbers. And we actually find the volcanics all over Jackson Hole. Phillips Pass has quite a few volcanics that you can see. Near the Elk Refuge on the Wildlife Museum, there's also lots of there's volcanics that are exposed there. And the reason they're on top of the existing rocks because they flowed on the topography that existed 8 million years ago. And so they've certainly been eroded many places, but they're preserved just because of where they landed topographically. I'm not sure if that answers the question or if you want to add something, Cynthia.
Faulting.
Or John.
Yeah, there's a lot of faulting associated in that Teton Pass area. And so things can look like they're lower, but they're just faulted down, basically, or other things are faulted up.
Yes, and somebody sent in info on the age of the Dolomites, and they're 250 million years old, so they're 250 million plus.
Permian.
Permo-Triassic, somebody says. So 200 to 265. So they straddle the Great Dying Event, the end of the Permian extinction event. Let's see. But you might also comment on the age, since you mentioned it, Cynthia, I think, of the dike in Mount Moran.
Oh yeah, that's about 755 million years old.
And the dike is actually a fascinating feature, and you can see it in the Middle Teton, you can see it in Mount Moran, and these dikes are associated with the breakup of Rodinia, the supercontinent that preceded Pangaea. And so it's an important geological historical marker.
Yep.
They're very striking.
And you can see chilled margins along the edges of them when you walk right up to them. They're worth a trip in and of themselves.
Yeah, if you look at the geologic map of Grand Teton National Park, the dikes are shown as red lines, and you actually see them scattered throughout Grand Teton National Park and beyond.
Right.
So there was a lot of volcanics. The one in Mount Moran is by far the thickest. You know, it's about 30 meters thick, I think, so 100 feet thick.
Right. And they run for miles and miles. I mean, we're just looking at a teeny little piece of it, but these things, if you could trace them, they would go for a long ways.
Yeah, and you can see that on the geologic map. You can see the one on Mount Moran go back a long, long ways until it disappears underneath the Limestones and Dolomites of the Paleozoics. So it probably goes a lot further.